Welcome back to the deep dive. We've got a stack of research here today that honestly feels a little bit like a heist movie.
It really does, yeah.
Except instead of stealing diamonds or cash, the researchers are stealing or, well, maybe borrowing is the polite term, intelligence from one AI to teach another.
Borrowing is definitely a safer way to phrase it. But yeah, it's a wildly clever workaround. We're talking about LLaVA today.
LLaVA, that's LLaVA, Large Language and Vision Assistant.
Right.
And the headline here for you listening isn't just that it's another chatbot. I mean, we see new chatbots basically every week at this point.
Oh, at least.
The real headline is how they built it. Because usually, to build a really smart AI that can both see and talk, you need millions of dollars. You need massive infrastructure and an army of humans labeling data.
Exactly. You need people sitting in a room, staring at photos for hours, writing down things like, this is a cat, or the cat is sitting on a red mat.
Which sounds awful.
It is. It's slow, it is highly expensive, and frankly, it is incredibly boring work for the humans involved.
But the team behind LLaVA, these are researchers from UW-Madison, Microsoft, and Columbia, they basically asked a totally different question. They asked, what if we just didn't use humans at all?
Right. What if we used an existing AI to teach a completely new AI how to see?
And the result of that mission is fascinating. It's a model that connects the visual world with the deep reasoning power of a large language model.
It's a huge leap. It is the difference between a computer that can just slap a label on a photo and a computer that can actually chat with you about the vibe of that photo.
So let's rewind a bit. Before we get into the how and the what, we really need to understand the problem. Why was this even necessary? Because we already have computer vision, right? Like, my phone knows when I take a picture of my dog, it groups all those photos together automatically.
It does, yeah. And that is the status quo right now. We have excellent vision encoders. Think of these as the eyes of the machine.
Okay.
Models like CLIP are the gold standard here. They are fantastic at detection. They can look at a bunch of pixels and confidently say dog or car or sunset.
So we have the eyes. The hardware, so to speak, works.
Exactly. And then on the other side of the room, we have the brains, large language models, LLMs like Llama or GPT-4.
Right, the ones everyone is talking about.
Right. And they have read the entire internet. They know history, coding, law, medicine. But until recently, most of them were entirely blind. They were text only.
So to use an analogy here, it's like you have a genius sitting in one chair who has read every book in the Library of Congress but is completely blind.
I like that, yeah.
And in the other chair, you have this observer who has perfect 20/20 vision, can spot a bird from a mile away, but they can only speak in one-word labels.
That is a perfect way to put it. You have a blind genius and a mute observer. And the core goal of visual instruction tuning, which is the specific breakthrough in this paper, is to finally introduce these two characters to each other.
To get them talking.
Yes. We want to wire the eyes directly to the brain so the genius can actually see the world and talk about it fluently.
Now, I know there have been attempts to do this before LLaVA. If you follow this space, you've probably seen things like Flamingo or EP2 in previous research. So why weren't those the final answer?
Well, we have seen them, and they are genuinely impressive engineering feats. But there was always this, they call it a fluency gap.
Okay.
Those earlier models were trained on massive data sets of image caption pairs. So if you showed them a photo of a dog and asked, write me a poem about this dog, or why does this dog look so sad? They often just choked.
They just freeze up completely.
Or they revert to what they know. They might just spit out, a dog on the grass.
Yeah.
They couldn't follow complex instructions. They were effectively stuck in caption mode.
I see.
To get them out of caption mode and into chat mode, you need a totally different kind of training data. You need instruction following data.
Which brings us right back to that bottleneck we started with. To get that data, you need thousands of examples of a human asking a nuanced question about an image and an expert giving a really detailed, thoughtful answer.
And nobody had that data set. It just didn't exist at this scale. Collecting it from humans would take months and cost an absolute fortune.
So this is the part of the paper that I found just the most ingenious, and honestly, it's the part that feels a little bit like cheating, but in the best possible way.
It really does.
The researchers decided to just create this data set synthetically. They used GPT-4 to generate it. But wait, we have to clarify something for the listener. At the time this research was happening, GPT-4 couldn't see images either. It was still the text-only version.
That's right. It was strictly a text-in, text-out model.
So walk me through this slowly. How exactly does a blind text model generate training data about images it can't even see? That sounds like asking me to describe a painting I've never looked at.
It sounds like a total paradox, doesn't it? But they used this really smart trick involving symbolic representation. They took an existing, well-known dataset called CUCO.
Cocoa, like the
Right.
hot chocolate.
Capital C-O. It stands for Common Objects in Context. It's a very standard data set in computer vision. Now, COICO images already have some basic metadata attached to them from years ago. They have simple captions like a man holding a bat.
Right.
But crucially, they also have bounding boxes.
Bounding boxes are just the coordinates, right? Like the man is in this square defined by these X and Y coordinates, and the bat is in that square.
Exactly. It's a numerical layout of the scene. It basically turns the visual image into geometry and text labels.
Oh.
So the researchers fed that purely text data, the captions and the coordinates, into GPT-4.
Wow.
And they essentially told GPT-4, hey, I want you to imagine a scene where there is a person at these specific coordinates and a bat at these coordinates. Now, pretend you're looking at it and write a conversation about it.
That is wildly clever.
Yeah.
It's exactly like describing a movie set to a screenwriter who can't see the stage. You tell them, okay, the hero is on the left, the villain is on the right, there's a ticking clock right in the middle.
Yes.
And then you just ask the screenwriter to write the dialogue based on that spatial layout.
That is a fantastic analogy.
Mm.
And because GPT-4 is so good at reasoning and understanding context, it could hallucinate in a good, heavily controlled way what that conversation would look like.
So give me an example. If the text data just says person, suitcase, and car, what does GPT-4 actually come up with? Does it just say the person is near the car?
No, it goes much deeper than that. It infers the broader context. It might generate a question like, what is this person likely doing?
Huh.
And then answer its own question with, they're probably packing for a trip or loading luggage into a vehicle.
Oh, wow.
It connects the dots between those isolated objects to create a full narrative.
So it's creating depth where there was only raw data. It's like turning a load of ingredients into a full recipe.
Precisely. And they asked GPT-4 to generate 3 specific types of content to train LLaVA. First was conversation, just straight up Q&A between a user and an assistant about the image. Second was detailed description, painting a really rich, comprehensive picture with words. And third was complex reasoning.
The reasoning part feels key. That's the why and the how, right?
Exactly. Things like, why is the cat looking at the bird? Or what happens if the boy kicks the ball? It forces the model to think about logic and cause and effect, not just pixels.
And they did this at scale.
Huge scale. They generated 158,000 of these unique samples. They essentially wrote an entire textbook on how to talk about images without a single human writing a line of dialogue.
Okay, so now they have the textbook. They have the ultimate training data. Let's talk about the student receiving it. What is LLaVA actually made of? If we pop the hood on this thing, what would we see?
The architecture is surprisingly simple, which is very often the mark of good engineering. It's kind of like a Frankenstein monster, but a very elegant one.
Okay, I like that.
They took a vision encoder, CLIP, specifically the VITL14 version, and that serves as the eyes. And then they took a language model called Vicuna to be the brain.
We've actually discussed Vicuna in other deep dives. That's the open source model based on LLaMA, right? It's known for being very chatty and capable, but it's much smaller and more efficient than GPT-4.
Correct. It's a very solid open source model. So you have CLIP as the eyes and Vicuna as the brain. But here is the major problem. They speak completely different languages.
Right.
CLIP outputs pixel features.
Yeah.
These are complex mathematical vector representations of visual data. But Vicuna only understands word embeddings.
So you can't just plug an HDMI cable into a book. They aren't compatible formats.
Exactly. You need a translator.
Yeah.
So the team added a projection layer. Technically, it's a simple linear layer. Think of it as a universal translator that takes the visual signal from CLIP and mathematically projects it into the exact same embedding space that Vicuna uses for words.
So to Vicuna, the image just looks like
another sentence.
Yeah.
Yes, that is the key insight of the whole architecture. To Vicuna, those image features just look like a sequence of tokens or words at the very start of the conversation. It essentially treats the visual input as if someone had just spoken a very dense, descriptive sentence in a language it already understands perfectly.
That is brilliant. And then they train it. How does that process work? Is it just one long, grueling training session?
It's actually a 2-stage process. Stage 1 is called feature alignment. In this stage, they freeze the eyes in the brain, meaning they don't let CLIP or Vicuna learn or change at all. They only train that connector piece, the projection layer.
Just calibrating the translator, making sure that the concept of cat in image speak perfectly aligns with cat in word speak.
Right. They use massive amounts of basic image-text pairs just to get the two distinct parts on speaking terms.
Yeah.
And then comes stage 2, which is the visual instruction tuning. This is where the magic really happens.
Okay.
They keep the vision part frozen, but now they update the projection layer and the Vicuna language model using all that synthetic conversational data they got from GPT-4.
Ah, so this is where it learns to actually be an assistant.
Exactly. This stage teaches the model not just, this is a dog, but here is how to answer a user's specific question about the dog in a helpful, conversational, human way. It learns the style of interaction.
So that's the theory. That's the recipe for how they built it. But obviously, the proof is in the pudding. Or, in this specific case, the proof is in the extreme ironing.
I love this example so much. This was one of the qualitative tests they ran to see if the model actually understood what it was looking at rather than just laboring it.
So for the listener who hasn't seen the paper in front of us, they showed LLaVA and some other baseline models a picture of a man ironing clothes. But he is standing on top of a moving taxi.
It's a totally ridiculous image. It's apparently from a niche sport called extreme ironing, and this is a great test because it separates the basic robots from the slightly smarter robots.
Right, because when they showed this image to a standard model like LLaVA, what happened?
LLaVA looked at it and said something along the lines of, a man sitting on the back of a yellow cab.
Which is technically true. It's factually accurate. The man is there. The cab is yellow.
It's factual, sure, but it's socially blind. It completely misses the weirdness of the situation. It misses the whole point of the image. It's like if you saw a clown at a funeral and just said, there is a person with red hair.
You're completely missing the context.
Exactly.
And LLaVA, how did LLaVA handle that exact same image?
LLaVA looked at it and immediately said, the unusual aspect is a man ironing clothes on the back of a minivan or van. But then it went even further. It explicitly noted that this setup is unsafe and unconventional.
It had an opinion. Well, sort of an opinion. It understood the broader context of human safety and social norms.
That is the reasoning part kicking in. It's not just listing objects in a vacuum. It's synthesizing the situation. It realized that ironing plus moving car equals bad idea. And that requires world knowledge, not just image recognition.
There's another example in the paper that I think really highlights the profound difference between just seeing and truly understanding. The chicken nugget map.
Yes. This is a classic internet meme where someone arranged a bunch of chicken nuggets to look roughly like a map of the Earth. And the text superimposed on the image says, sometimes I just look at pictures of the Earth from space and marvel at how beautiful it all is.
Now, if you are a literal machine, you are very confused by this. You see chicken nuggets, but the text explicitly says Earth. It's a direct conflict.
Exactly. Standard models very often hallucinate here. They might say, this is a picture of the Earth because the big text tricked them. Or they might just say chicken nuggets and completely ignore the text. But LLaVA actually explained the joke.
You got the joke.
It did. It said, the meme playfully suggests that the chicken nuggets represent the Earth. It understood the irony. And to understand humor, you have to understand both the literal reality of the image and the abstract intent of the creator. That is a massive leap for a machine.
But the example that really blew my mind, and I honestly think has the biggest implications for the future of AI overall, was the Elon Musk example. This one felt straight out of science fiction.
This is where we see what we call emergent behavior. This is the stuff that keeps AI researchers up at night, in a good way.
So they showed LLaVA a picture of Elon Musk. But it's not a normal headshot. It was a meme where he is dressed up as Doge, the cartoon dog.
And here's the kicker. The researchers explicitly state in the paper that Elon Musk was not in the training data for the visual instruction tuning. They never showed LLaVA a picture during that crucial second training stage and said, this is Elon Musk.
How on earth did it know? Because it identified him immediately. It said the name of the man in the photo is Elon Musk.
This is the raw power of connecting a vision encoder to a massive pre-trained language model. Vicuna the brain in this setup has read the internet. It knows who Elon Musk is. It knows he is heavily associated with the Doge meme.
So the vision part just had to provide enough of a visual hint.
Right. The vision part, CLIPP, probably passed along latent features like face shape, male, maybe even some specific resemblance vectors.
Yeah.
But Vicuna is the one that put the puzzle together. It basically thought, okay, face features maps this guy, context is Doge, therefore that must be Elon Musk.
That implies there is a massive amount of latent knowledge hidden in these LLMs. They know things they don't even know they know until they actually see them.
Exactly. It's like if you read a million detailed descriptions of an elephant but had never actually seen one. The very first moment you see a picture, everything just clicks into place. These text models are sitting on a treasure trove of information that is just waiting for the right sensory input to unlock it.
It also showed some incredible aptitude for coding, too, didn't it? This wasn't all just about memes and extreme ironing.
It did. They showed LLaVA a really rough sketch of a website, just a quick scribble on a napkin, basically. It said something like, put a joke here, put a button here.
And it wrote the actual HTML.
It wrote the HTML and the JavaScript to make a fully working website that perfectly matched the drawing. It recognized the rough layout, understood the human intent behind a drawn box, oh, that means a button, and translated that visual intent into executable code.
That is multimodal reasoning at an incredibly high level. It's translating from visual idea straight to logical code. But we do have to be rigorous here. Qualitatively, these stories are great. It feels very smart. But how do you actually grade a chatbot that sees? You can't exactly just give it a standard multiple choice test. Or can you?
Grading is notoriously difficult because open-ended conversation simply doesn't have one single right answer. If I ask you to describe the room you're in, there are 1,000 valid ways to do it. So the researchers went back to their original teacher. They used text-only GPT-4 as the judge.
The teacher grading the student?
Right. They would feed the user's question, the factual ground truth description of the image, and LLaVA's generated answer all into GPT-4. Then they'd ask GPT-4 to rigorously rate the helpfulness and accuracy of LLaVA's response on a scale of 1 to 10.
And the final score?
LLaVA achieved an 85.1% relative score compared to GPT-4's own capabilities on synthetic datasets. Considering LLaVA is open source and significantly smaller in parameters, that is incredibly impressive. It is punching way above its weight class.
But they also ran a much more objective benchmark, too, something called Science QA.
Yes, Science QA is a strict data set of complex science questions. We're talking diagrams of biological cells, physics problems with ramps and pulleys, detailed charts. On that, LLaVA achieved 90.92% accuracy.
That's remarkably high. That's a solid A grade.
It is. But they did something even cooler to push it further. They used a technique called ensembling.
Meaning 2 heads are better than 1.
Exactly. They ran the science question through LLaVA, which can actually see the diagram, and through GPT-4, which can only read the text of the question. When the two models disagreed on the answer, they used GPT-4 as the final judge to decide who was right based on the context, and that pushed the accuracy to 92.53%.
Which was a brand new state-of-the-art at the time.
It shows that while text-only models still have superior deep reasoning for some things, they desperately need that visual grounding. When you combine the eye of LLaVA with the massive brain of GPT-4, you really get the best of both worlds.
Okay, so we've been singing its praises for a while now, but as always, we have to talk about the limitations. It is not perfect. The paper mentions something called the bag of patches problem, which sounds like a quilting error, but I suspect it's a bit more technical than that.
It's a really great term for a very specific type of AI hallucination. It refers to a deep limitation in how the vision model actually perceives the physical world.
Give us the yogurt example. This one made me laugh, but it also really shows the danger here.
So they showed LLaVA a photo of the inside of a fridge. Inside, there was a large tub of plain yogurt, and sitting nearby on the shelf, there was a container of fresh strawberries.
And the user asked the model, is there strawberry yogurt?
And LLaVA very confidently said yes.
Ah, I see what happened. It saw strawberry, it saw yogurt, and it just mashed them together in its head.
Exactly. It perceived the image as a bag of patches, a loose, disconnected collection of visual features. It correctly saw that the ingredients were present in the frame, but it completely failed to understand the spatial relationship between them. It didn't verify if they were actually combined in a single package.
It missed the nuance. It saw all the parts, but didn't quite get the sum of the parts.
And because the language model side of it is so fluent, it answers incredibly confidently. That is the real danger of these models. They sound so sure of themselves, even when they're hallucinating connections that just aren't there. If you are relying on it to check for severe food allergens, that mistake really matters.
It also struggles with resolution, right?
Yes, the CLIP encoder processes images at a relatively low resolution by modern standards. If you have a photo of a document with tiny text, or a small label on a bottle, LLaVA might not be able to read it simply because the eyes aren't sharp enough. It's like trying to read a book across the room without your glasses. The brain is totally willing, but the eyes are just too blurry.
So, Zooming out a bit, we've got a model here that learns entirely from another AI. It can spot Elon Musk in a meme without being taught, and it can write code from a napkin sketch. Why does LLaVA matter in the grand scheme of AI development? Is it just a cool parlor trick?
I think it's much, much more than that. There are two huge takeaways here for the industry. First, it fundamentally democratizes multimodal AI.
Because you don't need the billion-dollar budget anymore.
Exactly. You don't need to hire 10,000 people to manually label data. You can just use existing powerful text models to generate the training data you need. It proves that synthetic data using AI to teach AI is a highly viable path forward that radically lowers the barrier to entry. It means university labs and small startups can suddenly build models that compete directly with the tech giants.
And the second big takeaway.
It completely changes what we expect from computer vision. We are permanently moving away from static tags. We aren't just tagging images with nouns anymore. We are moving toward deeply interactive, reasoning-based assistants.
It's the difference between a tool that just tells you this is a sink and a tool that says that sink is leaking and here's exactly how you fix it.
That's the dream, a true assistant. And LLaVA shows that we are much closer to that reality than we thought, simply by wiring up the existing tools we already have in smarter ways. We didn't actually need a massive new breakthrough in neural network math. We just needed a much better way to connect the eyes to the brain.
It really brings us back to that Elon Musk example for me. If LLaVA could recognize him without being explicitly taught to see him, just based on the vast knowledge hidden in its language brain, it really makes you wonder what else is in there.
That is the big question going forward.
Like, what other knowledge is just sitting dormant in these massive language models, waiting for the right pair of eyes or maybe ears or tactile sensors to finally unlock it?
We might find that our language models are already world-class experts in fields we haven't even thought to test them on, simply because we haven't given them the right sensory input yet. We are really just scratching the surface of what's already inside the box.
A truly fascinating thought for you to explore on your own. That is it for this deep dive into LLaVA. Thanks so much for listening, and we'll catch you on the next one.